Railways delivered the power to move people, freight, armies, raw materials, the power to move huge loads, and the technology to be fast. In this episode of Power, we investigate the high-speed trains that link cities, the futuristic visions of magnetic levitation and pods, and tell the story of engineering marvels from the longest train to the miniature wonderland. This is the story of rail power. Speed. Almost 200 years since trains became familiar intruders on almost every landscape, the sight and sound of steam has become a romantic memory. Replaced by more efficient, more powerful, more reliable, less polluting forms of power. Replaced above all, in the name of speed. This is the Shinkansen, the bullet train. Not quite faster than a speeding bullet, the Shinkansen redefined intercity rail travel for the modern age. Shinkansen is actually the name of the rail network across which the high-speed trains travel.
They decided to build a completely separate railway, and the word Shinkansen means new trunk line, giving you the idea that it's a separate railway altogether.
A network that revolutionised domestic travel in Japan and set the standard for high-speed rail travel in the second half of the 20th century.
More passengers travel by train in Japan than anywhere else in the world. Sells more tickets, about 1 billion tickets a year.
The first bullet trains began their journeys in 1964, linking Tokyo and Osaka. This line, the Tokaido Shinkansen, remains the busiest fast train line in the world. Over the years, a number of different train sets have entered service. The technology has evolved, as has the design. Aerodynamically refined in wind tunnel testing. The current Shinkansen have a maximum operating speed of 320 kilometers per hour, though they could go faster.
Another key challenge with high-speed train aerodynamics is how trains interact when they're passing one another, and also how they enter into tunnels. So the nose shape on trains can be very different, and it depends on how they're going to be used and the environment they're going to be used, because there's a range of aerodynamic effects that are really important in the design of the train. So if you look at some of the trains around the world, some of them seem quite blunt and some of them are more streamlined, like a ICE3, and then others almost have a duckbill type shape, and that's got to do with the environment that they're going to be operating in.
All Shinkansen are electric multiple units, with the most striking of current designs being the H5, the latest of the 700 series that features the duck-billed nose, an aerodynamic shape which reduced the piston effect, the force of air displaced as the train surges into tunnels.
So when a train enters into a tunnel, it can create a very high pressure wave, and that can cause all sorts of problems, and that pressure wave can also propagate down through the tunnel. So some trains are actually designed to limit or reduce that pressure wave. So when you see duck-billed type trains, it's designed for that purpose.
Aboard these trains, 3 classes of comfort speed passengers to their destinations. Grand Class, Green Car, which is the equivalent of business class, and Ordinary Class. Like almost all Shinkansen, the H5 draws power from overhead wires by means of a pantograph. In the context of railway operation, a pantograph is a device for collecting electrical current. The power supply is carried in overhead wires, and contact with the pantograph's metallized carbon strips draws power to the unit's drive system. For low-speed vehicles, trams, slow trains, trolley buses, the pantograph uses springs and air Air pushes the cylinder, which raises the pantograph into position. Springs then maintain contact with the wire. For high-speed units, such as the Shinkansen trains, springs are not efficient, and contact is maintained through a pressurized air system that holds the contact in place through constant force. From the 1960s onwards, the very fast train concept has developed on intercity routes in most parts of the world. But it is a very different type of power source that drives the train that holds the record for speed. That record belongs to a train that does not travel on rails. In fact, it doesn't travel on anything. This is the maglev. Maglev, magnetic levitation, uses the principle of magnetic attraction to both lift and propel the trains. Lift removes friction, maintenance is reduced, wheels are not worn out, and speeds can be tremendous. The record stands at over 600 kilometers per hour.
Japan has been developing a magnetic levitation railway for a number of decades now. And interestingly, there is a test track that you can go to see the train rip by once a day at close to 600 kilometres an hour.
There are regular maglev lines in China, Japan and South Korea, with others in development. A maglev system depends on two technologies, the power supply and the suspension. In some systems, a single technology provides both levitation and propulsion. Electromagnets powering an onboard linear motor. But other systems levitate the suspension system but do not propel. EDS, or electrodynamic systems, use superconducting electromagnets, or strong permanent magnets, to create a magnetic field, which induces currents in metallic conductors to push and pull the train towards its designed levitation position. Such systems require a separate propulsion source. Some EMS, or electromagnetic systems, can both power and levitate. Onboard magnetic fields interact with metallic loops set into the walls of the maglev guideway. The loops are made of conductive materials, and when a magnetic field moves past, it creates an electric current that generates another magnetic field. Different types of loops perform three important tasks. One type creates a field that makes the train hover about 12 centimetres above the guideway. A second keeps the train stable horizontally. The third is a propulsion system run by alternating current power, where both magnetic attraction and repulsion are used to move the train car along the guideway.
Principle of magnetism. Everyone's played with magnets, and they know that if you put the North Pole and the South Pole together, they attract each other. And if you turn them around and you try and put the North Pole and the North Pole together, you can't. They push each other apart. And so they use that principle, except they use electromagnets to cause the train to be held in the air.
The concept of the magnet design means that the only source of friction is air, and the result is a smooth trip at any speed. Unlike other attempts at evolving high-speed rail transport, experiments with power systems that have been abandoned. Trains run on rails, that's why they're called railways. But inventors have been attracted by the idea that trains encountering no friction would be efficient, fast, and quiet. We have seen that the maglev effectively suspends the train above the track, keeping it there through magnetic attraction. Hover trains used a similar principle, suspending the train so that the only resistance it meets is movement through air. Instead of magnets, hover trains employed the cushion of air concept that was developed for and is still the basis of hovercraft. The RTV, Research Test Vehicle 31, was a British experimental train. Work started in the 1960s and accelerated when the hovercraft principle was married to a second British invention, the linear motor. Eric Laithwaite began developing the linear induction motor, LIM, in the late 1950s. LIMs provide traction through the interaction of magnetic fields on the vehicle and a fixed external conductor. Such a motor eliminates the need for physical contact with the track, has no moving parts, and so lends itself to the hovercraft concept. In Laithwaite's original design, two sets of windings positioned a few centimetres apart were positioned so that an aluminium stator plate would fit the gap between the windings, the forces pulling one set of windings towards the plate and thus balanced by the opposite forces in the other set. The hover principle ideally requires a smooth surface so that the cushion of air contained by the skirt has minimum leakage. The hover train was designed to run on a concrete track, and a development track was built early in the 1970s. In 1973, RTV-31, the first vehicle to test all of the innovations, made its first run. The train travelled at 167 kilometres per hour over the 1 mile, 1.5 kilometre track with great publicity. But meanwhile, development had been progressing on the advanced passenger train for intercity transport. Arguments about cost, speed and efficiency went back and forth, but in the end, the hover train project was cancelled and the APT system was adopted.
Now nearing the final stages of its development, the French aero train will be a considerable boon to intercity commuters when it's brought into service.
The aero train, France's rival to the British hover train, used a similar principle, but like the RTV-31, was mothballed by the government in favour of a fast train that travelled on rails in France, the TGV. Before its cancellation, a number of test trains had been built with different power plants. Several of them were large enough to take passengers. The Aerotrain 02 was powered by a Pratt & Whitney turbojet, the S44, a full-size passenger-carrying car intended for suburban commuter service was equipped with a linear induction motor. And the Aerotrain I-80 was a full-size passenger-carrying car for intercity service. The growth of railways to their present status as mass transit transport systems in every part of the world did not, of course, rely on these exotic experiments. Everywhere, the workhorse for passenger and freight has been the diesel or diesel-electric locomotive. Despite their names, diesel trains are not driven by the power of their diesel engines. They are driven by electricity. The diesel engines power the shaft that drives the generator that powers the large electric or traction motors that turn the wheels.
The diesel engine does not produce mechanical motion directly to create the motion of your locomotive vehicles, but it's used to generate electricity, and then electricity is used to run the AC motor, then you go forward. Diesel engine can be optimized at a fixed engine speed and fixed operating condition. That's how you get the best efficiency.
Typical of the most powerful of the diesels is the AC 6000 CW, generating 4,500 kilowatts or 6,000 horsepower. The only units that produce more power are dual engine designs. These are the great machines that haul the huge loads, the ore train's massive freight loads. The versatility of the power source means that the power spectrum is wide. The first regularly operating diesel locomotive produced 883 kilowatts of power. The robustness of the diesel and its fuel efficiency compared to the standard internal combustion engine explains its ascendancy in railway, marine and heavy road applications. But there are drawbacks: the cost and availability of the fuel, the need for regular maintenance, the environmental issues of noise and smell. Where the pros and cons have been weighed, many operators have preferred systems that deliver electricity direct to the train's motors without the need for diesel generation. As with the Shinkansen, this means connecting the train to a live supply, either by an overhead wire or a live rail. The first electric train was demonstrated in Berlin late in the 19th century. It achieved a top speed of 13 kilometres an hour. The technology has advanced since then, and power is now produced in abundance. The power is generated not on board through a diesel engine, but by plugging the railway into the national electricity supply. The Shinkansen, the TGV in France, the Eurostar that links Great Britain to the continent of Europe, are some of the high-speed types of train that derive their power directly from a live source. France's TGV, Très Grande Vitesse, or very high speed, is a typical electric train.
They're fast. The track is built with that train in mind. So the track has to be long radius curves and not rough, but a smooth track. I think the engineering innovation is the design of the whole system to be reliable, to be fast and to be safe at the same time. So that was a rethink of railway technology.
Sleek, streamlined, some even with the duckbill that was first seen on the Shinkansen. The TGV network links every part of France and France with its neighbours. The service was initiated in the early 1970s, and the original concept was for gas turbine power. The oil price crisis of the period put paid to that. Electric traction became the power of choice. And though the look of the locomotives and their performance has progressed since the service was initiated in 1981, the basic principles that get the power to the wheels have not. The TGV's traction components include the pantograph, which maintains contact wire pressure at about 70 N. The main transformer, which converts 25 kilovolts, 50 hertz single-phase overhead power into 1500 volts, 50 hertz, and a number of parts that deliver this power to the traction motors. Thyristor-controlled rectifier bridges, the common block consisting of DC circuit breakers and the main filter capacitor, traction inverters that convert DC into a three-phase, variable frequency AC waveform combined to get usable power to the AC traction motors, which on the TGV are slung from the vehicle body, substantially reducing the mass of the truck, giving it exceptional tracking stability. Each motor can develop 1,100 kilowatts and can spin at a maximum rate of 4,000 RPM. This power arrangement has enabled the TGV to set the world's speed record for conventional trains. Line voltage had been boosted to 31 kilovolts and extra ballast tampered onto the right-of-way when on April 3, 2007, a modified TGV reached 574.8 kilometers per hour. Elsewhere in Europe, another very fast train, the ICE, Intercity Express of German railways, has, like other trains in the category, a distinctive nose shape to deal with the power it has as it pushes through the air.
You know, one of the challenges that we're looking at, in particular with the ICE3, is the slipstream effect of the train. So the ICE3 is just one example of a train where which is travelling at high speeds, and we need to understand how that train is going to induce flow behind it and how that flow is going to impact on surrounding infrastructure, for example. So the shape of the nose, which in the ICE3's case is also the shape of the tail, has a large effect on the flow that's induced. So we see a large downwash occurring, and that's associated with flow over the back of the train. And we can actually see large vortices, which are a little bit like tornadoes, if you like, on a different axis. And those vortices actually move around within the wake, and they can impact on different objects or on people as the platform goes through. So if you're looking directly behind the train, you have a vertical component of the velocity, so you have a downflow, and then you have that interacting with flows coming around the side of the train at the rear. And the way that they interact can be such as to introduce vortices. So you have the flow coming down through the middle of the train, and then you have a large rotation, and you get two vortices that a little bit like angled tornadoes originating from the rear surface of the train, and then they can move relative to one another, and they cause a lot of drag. They're associated with low pressure regions, and when you've got low pressure on the back of something, it's acting like suction, so it's pulling it back. And they're not dissimilar in nature to the vortices that you see behind a plane.
Other trains draw their electricity not from overhead wires, but from live rails. Perhaps the most famous of these travels beneath the streets of a city, the London Underground. When trains first started to run through tunnels beneath London, it was 1863, and power came from steam engines. The network, which continues to evolve, now covers more than 400 kilometres and carries almost 1.5 billion passengers a year, serving 270 stations and travelling at an average speed of 33 kilometres per hour. The first electric trains ran in 1890, and since the early 1960s, all London Underground trains have been electric multiple units, self-propelled carriages using electricity as the power source. A contact shoe beneath the rolling stock draws power from the live rail, which is the power source throughout the network. The onboard plant translates the delivered 750 volts of direct current and produces the power that drives the traction motors. The London Underground, known to all Londoners as the Tube, is the oldest underground system in the world. But the Seoul Metropolitan Area system in South Korea holds the record for route length at over 900 kilometres. The New York subway serves the most stations, 468. The busiest is the Tokyo Metro, with 3.3 billion passenger journeys each year. With its Art Nouveau stations, Paris may be the most decorative. And famously, the decor of many stations on the Moscow subway is of extravagant opulence. The technology is in place on many established lines, including the London Tube, for driverless trains. That future is already the norm in the Persian Gulf. The Dubai driverless metro opened in 2009. It covers less than 75 kilometres, serving 49 stations, with further expansion planned. What places it firmly at the forefront of technology is the fact that it is fully automated. Its trains are driverless.
The main thing it's known for is that it doesn't need drivers, and that's an increasing trend with new train systems. It's quite a comprehensive system running the length of Dubai.
Power is drawn, as with far older rapid transit systems, from a live third rail, delivering 750 volts of DC, powering trains on the Red Line at up to 47 and the Green Line at up to 38 kilometres per hour.
It's about 75 kilometres of track, and they're increasing that. It started operating in 2009. It's not an unusual type of metro system. A lot of it's elevated. I was there watching it being built for a while. One thing that's a little different to some of the other systems is that its power supply, it's obviously electric, is from a third rail and not from an overhead catenary. The problem with that is that you need to have a secure right-of-way so that people don't get in contact with the electrical circuits. The alternative is overhead catenary that uses a pantograph on top of the train to pick up, and that's certainly the system we see more of in most countries.
The power to move people in rapid urban transit has not always forced trains beneath the ground. Elevated trains may travel on raised rails, like Chicago's L. Maybe monorail designs from Disneyland and Tokyo to the Bangkok SkyTrain. Or they may be hanging trains.
Interestingly, railways don't have to be terrestrial in nature all the time. There are a collection of very interesting suspended railways where the carriages are actually hanging from an overhead rail.
The Wuppertal-Schwebebahn. The Wuppertal-Schwebebahn has suspended cars reaching speeds up to 60 kilometres per hour on a line running more than 13 kilometres above the streets of Wuppertal since 1901. The cars are suspended from a single rail built underneath a supporting steel frame with 486 pillars and bridgework sections. Each car hangs on wheels which are driven by multiple electric motors operating at 600 to 750 volts of direct current supplied through the conductor rail. The onboard power supply drives 4 direct current medium voltage motors per articulated train. Special trains have always had a special place in the affections of people. The Wuppertal-Schwebebahn is fondly known as the Old Girl. Trains associated with long, exotic journeys and spectacular luxury have a particular hold on the imagination. The extraordinary, futuristic and very expensive Shikishima is not a train to anywhere. It is exclusively a vehicle for taking short tours in northern Japan. A golden piece of modern design with Michelin menus, all suite accommodation and wonderful observation cars, this vision of tomorrow rides on a rather traditional diesel-electric power plant with a top speed of 100 kilometres per hour.
Japan's very interesting because there are this new breed of luxury trains, the Shikishima, which is ultra-luxury, Michelin chefs on board, beautiful state-of-the-art decoration, comfort, the technology underneath, the running gear, that the spring systems under the carriages are ultra smooth, and you never hear clickety-clack anymore and things like that. You've got a welded rail for a start. But the appointments inside these trains is something superb. But it's also the uniqueness, I guess the thrill of running on something that's a bit exclusive, something a bit special. Because luxury trains have always been the preserve of the ultra-rich.
The Indian Palace on Wheels is also a train dedicated to tourism. One of the luxury trains making journeys around the subcontinent, it takes its cue from the decorative traditions of princely India, the distant days of Maharajas and the British Raj. The Orient Express, a legendary name in train travel, is a luxury destination in its own right. In its heyday, linking Paris and Istanbul, the Orient Express was a powerful train that carried powerful people, heads of state, and every sort of celebrity for every sort of success and scandal. And in Agatha Christie's famous story, murder mystery.
Earlier 19th century, in order to realise a market that was there for the wealthy, but also to attract the middle classes to train travel. So the rise of trains like the Orient Express in the 1880s, essentially a very smart business plan to provide comfort and a quality accommodation on a train that you didn't have to change. So it was a matter of doing deals along the way with different governments across different borders to create one train heading across multiple borders.
Equally exotic, but a train with a real and vital communications role in joining the extremes of the world's largest nation, is Russia's Trans-Siberian Railway. The vastness of Russia can be understood by realizing that if Siberia was an independent country, it would be the largest country in the world. The Trans-Siberian, really a network of railway lines that link Moscow to Russia's Far East, is a journey of more than 9,000 kilometers. The longest railway line in the world. Building the line began in the 1890s and was completed in 1916, the year before the Russian Revolution.
Russia, interestingly, has a unique developmental railway story where the Tsar decided that he would have a different gauge when it came to the construction of railways on a large scale in that country, and randomly came up with 5 foot as a broad gauge, unique to his system. The Tsar broad gauge, it's referred to. And that, even though it caused all sorts of problems when it comes to transshipping at the borders with Poland and with China, ultimately, when the Trans-Siberian Railway got that far, it did create all sorts of bottlenecks when it came to the First World War and the Second World War. So it did do its job in helping to protect borders.
The Trans-Siberian is no tourist novelty. It continues to be the most important railway line in Russia. 30% of the country's exports travel on the line, and its connection to the Trans-Mongolian makes it an important outlet for Chinese exports to Europe. About 200,000 freight containers a year reach Europe on the Trans-Siberian. The fastest train on the route, which was fully electrified in 2002, takes just over 6 days to link Moscow to the Pacific Ocean. An average speed of 64 kilometers per hour across 5 time zones. After the Russo-Japanese War of 1905, in which inadequate railways meant the failure to reinforce the Far East, the Trans-Siberian received heavy investment, which paid off in the Second World War, when moving the Siberian Reserve to meet the German invasion was crucial to the Soviet Union's survival.
Here are 3 of many good reasons why there'll be a warm reception for the Nazis if they try an invasion.
Almost since the first train pulled the first wagon, trains have been part of military planning and military weapons.
It was the 1850s that also saw the first use of trains extensively in war, something that was to become a major theme for the next 100 years. Troops were brought to the front en masse by train in the Crimea War, helping to create one of those interesting things that we saw a lot of in the late 19th century and certainly through the 20th century, the stalemate of war, trench warfare, and the use of heavy artillery that could be brought to the front pretty quickly by train, creating massive war front and huge loss of life, of course. The American Civil War, effective use of trains.
During the American Civil War, volunteers from the Union Army commandeered a train and took it north. As they went, doing as much damage as possible to the vital rail line from Atlanta to Chattanooga. They were pursued by the Confederate forces at first on foot and later on a succession of locomotives. The event was reproduced in one of the great achievements of silent cinema, Buster Keaton's 1926 film, named for the featured locomotive, The General. Since that event in 1862, trains have often played a role in the massing of armies, their supply and support, and the carriage of heavy weapons. In the Second World War, with industry in America from coast to coast gearing up to be, in President Roosevelt's words, the arsenal of democracy, it was the railways that were vital to moving war materials and personnel to the ports, and so to the battlefields.
Then, railways allowed troops to be delivered to the front, like a sausage factory, continually.
And it was railways that made possible the carriage and the use of the largest caliber rifled gun ever used in combat, Showewa Gustav, Heavy Gustav. Originally designed to take on the fortified French Maginot Line.
You had some very interesting technologies developed specifically using railways. The massive rail-mounted armoured guns and cannons, which were as big as anything on a battleship, if not bigger, where they would fire 14-inch, 16-inch shells, I believe, as far as miles into the battle zone from track-mounted guns, recoiling great distances down the line as they fired these extraordinary salvos, much bigger than anything could be managed on conventional land arrangements.
Also produced by Krupps was the slightly smaller but far more practical K5, which could fire a 255 kilogram shell 64 kilometers at the rate of 15 rounds an hour. 25 of the guns were produced and they were used in France and in Italy. The limitation in sighting the gun was that its effective aim could only be achieved vertically, limiting the gun to targets in line. To track targets on a horizontal axis, either a curved length of railway was used with the gun shunted backwards or forwards to aim, or for 360-degree traverse, a turntable could be constructed, consisting of a raised rail section, the firing bed, which carried the gun, running on a circular track. It was the K5 that formed the basis for the M65 atomic cannon. Developed in the USA after the war and nicknamed Atomic Annie. Although based on a railroad gun, Atomic Annie was towed by special tractors and was capable of firing a nuclear shell.
So the M65, the Atomic Annie, or the atomic cannon, was very much a product of its time. This weapon was designed to be used by land forces to fire a small nuclear round, bomb, at enemy land forces and create what you'd call the nuclear battlefield. Well, this is quite an enormous weapon. Its caliber is, I believe it was 280 millimeters, which is the equivalent of an 11-inch gun. And its origins would have been from some of those very heavy artillery pieces that existed in the First World War and in the Second World War. And weapons of that size were originally mounted on railway carriages because that was the only thing that was strong enough to pull them around.
In military use, trains have not only been valued as a means of transporting weapons and manpower, they have been used for speed.
One of the uses of a high-speed rail track is to test the flight characteristics of a guided missile submunition. So in the very early developmental stages, they'll run a new missile down the test track. At the end of its travel, they can stop the sled dead, which will release the missile going forwards, and then allow it to impact with a target, and that way you can simulate in a very closed environment the impact of the missile with a target array.
The 846th Test Squadron of the US Air Force broke the world speed record for a vehicle travelling by magnetic levitation on a test track in Otero County, New Mexico, when a rocket-powered maglev sled reached a top speed of almost 1,020 kilometers per hour. The Air Force used superconducting magnets to move the sled without it touching the ground. The maglev system is the most recent rocket sled, and its speed record surpasses that of the sled that powered by 9 solid fuel rockets with 40,000 pounds of total thrust for 5 seconds that accelerated Colonel John Stapp of the US Air Force to a speed of 1,017 kilometers per hour at an Air Force base in New Mexico on December 10, 1954. Stapp, who was known as the fastest man on Earth, was not concerned with how fast a man could go, but what would happen to a man subjected to major G-forces on rapid acceleration. And he demonstrated that a human being can withstand 46 G.
Colonel Stapp, the fastest man on Earth.
From the start, the appeal of railways has been their ability to move large loads over long distances. power has been decisive in determining how large the load, how far the distance. In one great and barren part of the world, where distances are vast and loads enormous, the train is king.
The task for a heavy haul railway is the same the world over. You want the cheapest method of getting from mine to port. One way of doing that is to have the optimum number of locomotives and the optimum number of wagons with as much as you could possibly fit in, which comes down to how well your track is constructed for how much you can actually put per train.
In Western Australia, there are mountain ranges made of iron ore. The job of getting the ore from the mines to the ports is work for the longest and heaviest trains anywhere.
A long iron ore train, fully loaded, will take several kilometres to stop. It will stop quicker if it's on an uphill grade, and it will take longer if it's on a downhill grade. These are the simple Newtonian laws, and they apply to iron ore trains as well as everything else. So you need a really good braking system, and you need very powerful locomotives to get you up the grades. And it isn't a solely downhill run from mine to port. There are some uphill grades as well.
In the Pilbara region, ore trains typically approach 240 cars, or around 30,000 tonnes. The standard for Rio Tinto operations is 29,500 tonnes of iron ore, carried in a train 2.4 kilometres long, hauled by 3 locomotives. A BHP Billiton ore train has typically 268 cars and a train weight of 43,000 tonnes, carrying 24,200 tonnes of iron ore.
The skill in driving a fully loaded iron ore train is considerable, because if you accelerate or decelerate incorrectly, you could break the train. So if you're imagining you're going over a hump, you have to be careful that you don't put so much tension between the couplings of the wagons that could actually cause the train to break in two. So it's very difficult to drive such a train.
The record was set on the 21st of June 2001, when a train comprising 682 wagons with a total length of 7.352 kilometres, hauled by 8 6,000 horsepower General Electric AC 6000 CW diesel electric locomotives and controlled by a single driver, travelled the 275 line to Port Hedland in Western Australia. Each AC 6000 CW 6,000 horsepower, 4,500 kilowatt loco was powered by a V16 twin turbocharged engine. There is a spectrum in train travel, and here is the opposite end of it from the ore-carrying behemoths. This is Miniature Wonderland in Hamburg, Germany, the world's largest display of model railways. Construction began in 2000 and is set to continue into the future. The present scale of the operation is remarkable. More than 7,000 square metres of floor space house an exhibit that boasts almost 15,500 metres of track, along which more than 1,000 trains run through 1,300 signals. In a world populated by about 265,000 figures. The exhibit suffers the theft of about 3,500 every year. So far, building Miniature Wonderland has cost about 20 million euros and employs some 270 people. Included in the landscape is the world's largest model airport, an advanced automated system to move cars around the layout, and a control system operating through 50 computers. There is something fantastic about the world of the Miniature Wonderland. But there are even more fantastic, futuristic plans on the drawing board for train travel into the future. And the most futuristic thing about many of the designs is the power source that they will use. The hyperloop concept, in an advanced stage for Dubai and proposed as a high-speed link between cities such as New York and Washington, promises to revolutionize not just the speed, but the way in which we travel by train. The hyperloop concept operates by sending specially designed capsules or pods through a steel tube maintained in a partial vacuum.
One approach to ground transport in the future that's being considered is if you can have trains effectively or capsules operate in a vacuum, then you've removed the aerodynamic problem. Now, this is a really long way off, but if it was to work, that aerodynamics wouldn't be a problem, so you could achieve extremely high speeds.
The first thing to imagine afresh is the railway station. Pods constantly shuttle into and out of terminals, and passengers step on and on arrival step off the moving car. Each car with perhaps a capacity of 6 to 8 passengers. The original concept for the look came from Elon Musk, whose design envisages each capsule floating on a 0.5 to 1.3 millimeter layer of air provided under pressure. This thin layer provides a more achievable and more practical tubular concept than the original vacuum tube from which it has evolved. The vacuum tube, offering zero air resistance, could accommodate theoretical speeds of thousands of kilometers an hour. The thin layer buoys the pods while still allowing for speeds that wheels cannot sustain. Linear induction motors located along the tube accelerate and decelerate each capsule, with rolling resistance eliminated and air resistance greatly reduced. The capsules effectively glide for the bulk of the journey.
You remove the air, so you're removing the aerodynamic force, and so it's like travelling in space. Effectively, that's what you're trying to do. Create a little tunnel, space tunnel, but you don't have aerodynamic drag. Which is why you can travel so fast in space without having so many problems. Because if you were to travel at those sort of speeds that space shuttles travel at through the atmosphere, you would generate enormous amounts of heat.
The original Hyperloop concept placed an inlet fan at the nose of the capsule to transfer high-pressure air building at the front of the vehicle. Pods are projected to reach a top speed of 1,220 kilometers an hour, meaning that the journey from New York to Washington would be accomplished in just under half an hour. The story of power on the rails started with the search for a smooth journey and reduced friction. It continued with streamlining and improved ways of producing power, and with the Hyperloop, it reaches the points of almost eliminating friction, getting rid of rails and generating enormous speed, but requiring the expenditure of very little power. Pod cars, PRTs, or personal rapid transport systems and hover trains are on drawing boards and in some cases exist and are being tested in various parts of the world. In some places, typically airports like London's Heathrow, PRTs are already an important part of the transport infrastructure, as pod cars shuttle passengers between terminals, from terminals to public transport of car parking hubs. Designs that not long ago belonged in the realms of science fiction are now carrying paying passengers, and the power of the railway, transformed though it might be, shows no signs of diminishing.